A block of mass m is at rest on a frictionless inclined plane at an angle of theta equals 30 degrees from the horizontal, as shown in the figure to the right. The block m is connected to a second pulley of mass m, big M. Oh, that's like a programmer's nightmare, where the only thing differentiating the two variables is one is capitalized. By a massless string, right, an ideal frictionless pulley. Frictionless pulley. So does the pulley even spin? I wonder if the pulley... So the pulley probably doesn't have to be massless because the pulley doesn't even spin because the pulley is frictionless? I don't know. I'm going to assume that since they didn't give us a mass for the pulley, nor a radius, that we probably just ignore that portion. I think we do. Okay. What must the mass m be for the blocks to remain at rest? Okay, so the idea here, using this diagram, zoom in, zoom, we have I'm going to call this mass 1 and this mass 2, just because I don't like my small m's and big m's pretty much look the same. So I'm going to rely on 1 and 2 instead of small and big. So we have force due to gravity 1, probably should have a capital F, and then we'll have force gravity due to 2. So for it to remain at rest, there's going to be zero acceleration, which means that there is going to be the forces are going to be equal. So for zero acceleration, sum of all forces equals 0. So this force is going to cancel out that force, and this pulley is basically just changing directions. So Fg1 is going to be due to gravity, which will be mg sine of theta. And you might be like, wow, how did you get that sine of theta? Well, force gravity is straight down, and then you can use this angle theta and this and a bunch of geometry to basically derive that the force that's going to be pulling the block down is going to be the sine theta. And you might be like, well, how do you know that sine versus cosine? I would recommend just memorizing it. The mnemonic that I use is sine for sliding. So the force causing a block to slide will be sine sliding. And that's just a mnemonic I use because this scenario of a sliding block comes up enough that it's worth just memorizing. So this is going to be mg sine of theta. And then this will be equal to, and they're actually in opposite directions because they sum to 0, but you get the idea. Equals, this will be mass 1, this will be mass 2 times g. Okay? So, looking at this part of the equation, that part of the equation, canceling things out, we get, cancel out the g's, and we're trying to find m2, I think. m2 in terms of m1. So we're solving for m2. So we have m2 equals m1 sine of theta. Well, I think they said theta equals 30 degrees. 30 degrees, yep. So equals m1 sine of 30. We know what the sine of 30 is. That's 1/2. So m2 equals m1 over 2. Not too bad. Fairly reasonable. Okay, so we'll say B is the solution to that one. Okay, so now we got that part. Now we're going to suppose that we add a friction to the surface. So it goes from frictionless to friction full of the inclined plane using material with coefficient of static friction, mu of S equals 0.4, and mu of K for kinetic is 0.3. What is the maximum mass M can be for the blocks to remain at rest? Okay, so now we're still going to have these balance of forces here. So we're going to have on the left side, we're going to have so we're looking for the maximum M2. So the biggest, so it's going to be pulling down, which is going to be causing a motion in this direction. So we'll have M1G sine of theta plus, because force is acting this way, but we're also now going to have force of friction, static. And that will be mg cosine of theta times mu k. No, mu static, because we're before it can be to remain at rest. So remain at rest means it's static and it's going to stay static. Therefore, we're using the static coefficient of friction. If there was motion, then we'd use kinetic. So this is the forces pulling the block down. So this mg cosine theta, this is the normal force. So we have a normal force like this. This is mg cosine of theta. And the way I remember that is if this is sine theta, then perpendicular to it, it's reasonable to assume that it's going to be cosine theta. And again, you can derive this the same way by going mass times gravity this way, and then using similar triangles and various properties of angles and such. And you can eventually find that this force right here, the normal force opposing the force of gravity based on the inclined plane, will be mg cosine theta. I memorized that mg sine theta is sliding down the ramp, mg cosine theta is perpendicular. And that's what you want for the normal force here. Another way to kind of troubleshoot that to make sure it's correct is if you had theta equals 0, then you'd basically just have a flat level plane, and we kind of know that this is mg, this is just mass times gravity equals the force normal. Well, you could also think of it as mg cosine of 0, cosine of 0 is 1. So this seems semi-reasonable. Okay, and we're going to say that this equals, because we're at rest, staying at rest, this will be mass 2 times gravity. I probably should have 1s over here, 1, okay. And so we're trying to solve for mass 2, so we'll cancel the gravities, which kind of makes sense, the gravities would all cancel. So we can say mass 2 equals mass 1 times quantity sine of theta plus cosine theta mu static. And we know theta is 30, so this will be 1/2. This will be square root of 3 over 2, because we know the cosine of 30 is square root of 3 over 2. And so if we try to combine that, we'll have square root of 3 times static coefficient of friction is 0.4. We were just given that. Times 0.4 plus 1 all over 2, mass 1. Okay? See what our possible answers are. Okay, so I think they want us to solve this. Go to our calculator. Clear. I think I'll leave it in radians for now. Square root of 3. Not that it matters, because I don't think I'm going to use it, because I already did the conversion from degrees to a number for sine and cosine. Times 0.4 plus 1, that's the numerator, divided by 2. 2 is the denominator, and that gives us 0.846. 0.846, and this will be M1. So we have 0.846, which I think is this one right here. And that would be the maximum mass that the big M, the vertical block, can be for the whole system to remain at rest, given a static coefficient of friction of 0.4. Okay, so now one other thing to kind of keep in mind is the force of friction, it opposes motion. So in this case, the force gravity and force friction work together in the same direction, the sliding part of the block. But if the block was moving downward, force of friction would actually switch to being upward, because force of friction by definition opposes motion. That's just something to keep in mind. Okay, if the block on the inclined plane had not been at rest but moving at speed v initially, we want to maintain a constant speed. Constant speed means acceleration equals 0, which means the sum of forces equals 0. Mass m should be blank compared to the previous problem. Okay, so we can actually, might be easier just to find this. So the only thing that changed here is now it's moving, which means we're going to go from static to mu kinetic. So I can just rearrange this problem right here. Light blue it is. This would be mass times square root of 3 times 0.3 plus 1 over 2, which would give us, can I just go back up, back up, back up, back up? Nope. So again, square root of 3 times 0.3 plus 1 divided by 2. This gives us 0.79. I'm going to say 0.76. Yeah, I'm going to say 0.76. 0.76 m1, 0.76 is less than 0.846. And so let's make sure there's nothing tricky about the way it's phrased. Mass m should be less, decreased, compared to the previous problem. So if it's moving, we need a smaller weight on m2 to maintain the same speed throughout the whole endeavor, so to speak. And we could logically realize that just because the coefficient of friction is less for kinetic than static, which kind of makes sense. It's kind of hard to get something moving when you're pushing, but once it's moving, it's a little bit easier than that initial umph, so to speak. So, and for this problem, it's just easier because the way we wrote out the first part to look at the second part and be like, okay, the way we wrote out the second part, it's easy to look at the third part. Problem was it 13? 13. And we can kind of be like, okay, the numbers decreased when we plugged in the new value. Not too big a deal. That's how we approach this problem. Hope it helped. I will see you next time.